Yeah, thanks for the introduction and thanks for inviting me to this very cool place. I really enjoyed it so far. I'm going to talk about exactly this question: how much manifold topology can a topological quantum field theory see? And of course, I won't answer this for all topological quantum field theories, but I'll talk about a certain class of topological quantum field theories and how we can understand these. Before I'm going to say anything else, let me point out there's sort of two papers in the archive on this. The latter one is joined with Christopher Schommer-Priest. And in the end, if I have time, I'll mention some results that are ongoing joint work with Noah Snyder. And also a lot of the ideas and concepts in the end sort of arose from discussions with Theo Johnson-Freight as well, so he should also be mentioned. Okay, before I'm going to tell you what this talk is actually going to be about, let me briefly recall or say what I mean by a topological quantum field theory here for this talk. So what we are looking at is a category, a symmetric monoidal category of cobordisms. What does that mean? We have objects are closed, smooth n-1 manifolds, morphisms are diffeomorphism classes of compact n-dimensional bordisms, and the monoidal structure is disjoint union. And we can look at symmetric monoidal functors from this cobordism category into the category of vector spaces. Say objects are vector spaces, morphisms are linear map, and the monoidal structure is the tensor product. So in short, if you don't like categories, what this is really doing, it assigns to a closed n-1 manifold a vector space. It assigns to a compact n manifold a linear map, and this assignment is compatible with gluing of manifolds and with taking disjoint unions. All right, and so in even shorter, one way one can think about a TQFT is that a TQFT describes some sort of representation theory of manifolds. So that's sort of the idea what a TQFT is. And let me maybe add some decorations to this. In this talk, I am going to look at manifolds and cobordisms with some additional tangential structure. This could be a spin structure, orientation, and so on. For most of the talk, I won't need this. In the end, I'll sort of strictly need some tangential structures. So we're going to talk about some tangential structures. And as my target, for most of what I'm going to say, I will use the target of super vector spaces. So this is, I'm using CMOD2 created vector spaces, creating preserving linear maps. And now the symmetric monoidal structure uses the causal sign rule. So if I braid two fermions around one another, I pick up a minus sign. For the beginning of the talk, this will just be a technicality. All the results also work for vector spaces. In the end, this will be strictly necessary. So in the end, we really need super vector spaces. So now, let me sort of give a bit of context of what I'm going to talk about. A TQFT, as I said, is a sort of representation theory of manifolds. It's some way to assign numbers to manifolds. Whenever you have a way to assign something algebraic to something geometric, you should think of every one of such an assignment as being a sort of generalized geometric object. This is sort of the philosophy that we have behind sheaves and behind schemes, is whenever I have an assignment of algebraic data to geometric data, you can think of this sort of one of these assignments as a generalized geometric object, and you could ask, can I do geometry with it, right? And somehow the slogan of this talk, or the slogan behind this talk, is going to be, how can we study TQFT sort of in analogy to manifolds? And the sub-part of sort of the classification of manifolds that is going to appear here in this particular talk is surgery theory. So what sort of emerges from this talk during sort of at the end of this talk is a sort of surgery theoretical perspective on TQFTs. So can we do surgery theory with TQFTs? Can we classify TQFTs with something which is analogous to or dual to surgery theory? And I'm going to focus on a very particular class of TQFTs and a very particular sort of class of surgery, or a very particular sort of subset of surgery theory in this talk. But I think the philosophy that I want to get across is that you can sort of use various ideas from the study of manifolds, and there should be something dual on the side of TQFTs. Okay, so this is sort of the outline, but let me first sort of give some examples of TQFTs, right, sort of to get us all into this perspective. For example, a very sort of useful class of TQFT is also called invertible field theories. An invertible field theory, by definition, is it's sort of one that assigns, if I'm valued in vector spaces, to every n-1 manifold an invertible vector space, in other words, just the complex numbers, or a line, if you like, and to every bordism, it assigns a non-zero number, okay? And here is a way to construct invertible field theories, invertible-oriented field theories. What you give yourself is a class in Hn of BSON with coefficients in the units of our ground field. So this could be, I mean, in general, this is a characteristic class. This could be the Euler class. It could be Stiefel-Whitney classes. It could be Pontryagin classes. You can sort of base change them so that they live in C-cross. And what you then do is you look at the following assignment. To an n-1 manifold, you just give the trivial vector space And to a Bordism, you just record the sort of corresponding characteristic number. So you integrate this class over the Bordism, and that assembles into an invertible field theory. And more generally, you can say invertible field theories really encode classical Bordism invariants. The sort of things that people look at if they do classical Bordism invariants, you can encode these as invertible field theories. And so there's a question, yes?
Which dimensions is that?
So this is which dimension is this group non-zero?
Yeah.
This group is in all dimensions non-zero because you always have the Euler class, because this n agrees with this n. It becomes somehow, if you make the n here, if you make the n here much larger than this n, you get into the stable range where you just have the cohomology of BSO, and then it's, then you know what it is. And somehow the unstable one, you always have a non-zero group because you always have the Euler class sitting at that level.
No, when n is even.
So,
Always, you mean when n is even, it's always non-zero.
so Hn,
Class doesn't exist in all degrees.
the Euler class exists, the Euler number over a closed manifold does not exist, right? Or is just the Euler class? Yeah, no, you're right, of course. The Euler class doesn't exist. When n is even, it's, yes. Okay, sorry.
N even.
For n even, exactly, this is non-zero, there's the Euler class in there. For n odd, the Euler class, you're completely right, yes, exactly. I think in some cases then there's still a C mod 2 there, but yeah, okay, yes.
There's some torsion inside.
Yes, there's also torsion examples in there, yeah, exactly. All right, so, but the real question then is, if you do TQFT, if you don't sort of want to get away from these classical Bordism invariants, what can we do with non-invertible theories? And these non-invertible theories, they could potentially, hopefully, maybe, correspond to more exotic invariants, right? And we will see a class of non-invertible field theories later. Another class of non-invertible field theories that I won't talk about, but just to mention them, are sort of the state-sum quantum link invariant inspired theories. So things like Witten-Reshetikhin-Turayev theory, Tura-Vero theory, Crane-Yetta theory. These are all examples that give us non-invertible field theories. And so you could ask, what are the manifold invariants that I can produce from these guys that sort of go beyond, possibly go beyond classical Bordism invariants? And indeed, that's a question you could ask. If M is a closed n manifold, then set of Mn is, you can think of this as a Bordism from empty to empty, and that's a linear map from the ground field to the ground field, so it's a number. And by definition, I said the Bordism category for me contains smooth manifolds and smooth Bordisms, diffeomorphism classes of smooth Bordisms. By definition, this is a priori a diffeomorphism invariant. But of course, then the question arises, is it really a diffeomorphism invariant, or is it something much weaker? Does it, for example, just depend on the underlying Poincare complex? How much manifold topology can a TQFT see, right? And I want to answer this question for a particular class of TQFTs. Not for all TQFTs, of course. That's crazy. I mean, probably everything, I don't know. But I want to sort of focus on a particular class of TQFTs. And to explain what this class of TQFTs is, let me first go back to the basics and let me recall something that I think many of you will have seen somewhere, which is the classification of two-dimensional oriented TQFTs. So let's look at the two-dimensional oriented TQFTs, say valued in vector spaces. The data of this, what will you see? You will see whatever the TQFT assigns to the circle, that's a vector space. Let's call this vector space A. Then you have this particular Bordism, this pair of Pan's Bordism. This will give us a linear map from A tensor A to A. This disk Bordism here will give us a linear map from the ground field to A. And these together fulfill the axioms of an algebra. So here what we see is a unital algebra. In fact, a commutative unital algebra. Similarly, we get a coalgebra structure, and they fulfill this relation, the Frobenius relation. And so we found, or we see, that two-dimensional oriented TQFTs are the same as commutative Frobenius algebras. Okay? So that's nice and easy. This is 2 dimensions, but of course we care about higher dimensional manifolds. And if I give you a d-dimensional TQFT, the classification, if it's not extended or not derived or nothing, and really look at these sort of plain TQFTs, a functor from a Bordism category to the category of vector spaces, it's completely unclear how to classify these. But you can still extract invariants from such a TQFT. And one of these invariants is that whenever I have a TQFT, I can still look at the algebra assigned to the d-1 sphere. This will still have a pair of Pan's multiplication, which is given by take a large disk and cut out 2 smaller disks. That gives me a Bordism from 2 spheres to a single sphere. And it has a unit, and this is still a commutative algebra. If I'm oriented, it's still a Frobenius algebra. And this still retains a lot of interesting information about this TQFT. That's sort of part of what I'm going to say here. And of course, if I would work derived, if I would work with an infinity functor, what this really would be is an ED algebra. But for us, if D is large enough, this is just a commutative algebra. All right. And so what I was just saying is, if I have a D-dimensional TQFT, then this is an interesting algebra. Let me sort of first say a little bit how you can think about this algebra from a physics perspective. And this essentially comes out of the state operator correspondence. You should think of this algebra as sort of containing or encoding the local operators of my TQFT. Namely, very precisely, if I have a manifold, a d-dimensional manifold, and I have a bunch of points in this manifold, and these points are normally framed, so they have sort of a normal framing, and these normally framed points are labeled with vectors in that vector space. Then I can associate a number to that configuration, the partition function of this TQFT with that configuration. What does that partition function do? It takes this manifold with these sort of normally framed labeled points, and it does the following composite. It goes from the tensor unit or the ground field to, well, you first sort of just use these VIs, these labels. This gets into a big tensor product over these spheres, and then you take the rest of the manifold where you cut out a tubular neighborhood of all these points. And you do need to use this normal framing to identify this tubular neighborhood with a standard disk, so that the boundary is really a standard sphere and not some abstract sphere. And so this is the partition function, and so you can really think of this, the vectors in there as being the local operators, and the algebra structure encodes what happens if you fuse local operators, if you bring local operators close together. So that's the first piece of information. Okay. But this game you can continue to play. For example, let's fix some sigma, which is an arbitrary closed d minus k manifold. Right here, I'm just looking at point operators. I could now look at operators of sort of different shape, right? And then again, I could look at this algebra, set of sk minus 1. So now I notice that part of my slide is missing. That's unfortunate. Okay, let's see. Is there some way to... Okay, I think the problem is that this is online. Yeah, maybe I do it like this. Does that work? Yeah, okay. If you don't mind this, just ignore that side. Right. So what happens is you can now look at this algebra. So what I'm doing is I just look at the sphere cross sigma, and as a multiplication, I now use just the disk on the left, and then I just cross it up to the right dimension. So I sort of take this algebra and essentially compactify it along sigma, if you like. And you can think of this as the algebra of sigma-shaped operators. Namely, this is a vector space, and again, if I have a normally framed sigma sitting in my big ambient manifold, I can label this sigma sitting in this big manifold by a vector in this vector space and evaluate it to a number, which you can think of as the partition function of this big manifold, where you have the submanifold sigma sitting inside of it, and this submanifold sigma is sort of labeled by this operator living in that algebra. And again, I can look at this multiplication, and what this multiplication does is sort of what it tells us what happens if you fuse these sigma-shaped operators along a normal direction. That's the idea. Okay, good. So these are two algebras you could care about for any sigma. And we are going to particularly focus on two of these algebras that are important. Namely, we're going to focus on S2n-1, so I'm going to just focus on even-dimensional TQFTs now. So we are focusing on the even dimensions. And we can look at this algebra, and the other algebra that will be important is the middle dimensional sphere. So I'm looking at the Sn-1 shaped operators, and I'm looking at the point operators. Okay, these are the two algebras I'm going to care about. And I'm going to call it two n-dimensional TQFTs semi-simple if these two algebras are semi-simple algebras. So that's an algebraic condition, a representation theoretic condition I could just impose. The reason I impose this is that many, in fact, I think all higher dimensional TQFTs I'm aware of are semi-simple. So classes of TQFTs that are semi-simple, evidently invertible TQFTs are semi-simple. Just one-dimensional algebras, those are semi-simple. Unitary TQFTs, this is another example. If TQFT is unitary, if to a manifold it actually assigns a Hilbert space, a finite dimensional Hilbert space rather than a vector space. And to an oriented Bordism, what it does is if you take the orientation reversal of the Bordism, read it as a map, as a Bordism going the other way around, you take the Hilbert space adjoint. Such TQFTs will also always be semi-simple. Yes?
In the bottom half of your slide is 2n, and the top half of your slide.
That is correct. Yes, exactly. So this is always the top dimension. Yeah, that's right. Exactly. And another, now I got it right, another class of TQFTs, and this I think is the reason why most of the examples that we currently have, why they are semi-simple. If I start with a once extended TQFT, so TQFT that does not just assign vector spaces to n-1 or 2n-1 manifolds, but it also assigns algebras, say, to 2n-2 manifolds. And this is compatible with cluing along bimodules as well. Such TQFTs will always be semi-simple. And in fact, rather than algebras, you might as well also use linear categories or superlinear categories. The same applies. So a caveat here, when I say algebras or categories, I really mean the classical two-category of categories. So if categories functors and natural transformations, or if algebras bimodules and bimodule maps, and the tensor product is the ordinary tensor product. This situation will be different if you would look at derived TQFTs. If here you take sort of the correct derived category of algebras, or say DG categories down here. But then I think we don't have a single high-dimensional example of one of these TQFTs, which is defined on all cobordisms. And here we have examples. And somehow I think, just maybe sociologically, the reason most TQFTs we currently have access to are sort of fall into this class is that they have to be constructed somehow. And usually the constructions tells you that explicitly or implicitly they are extended, at least to sort of level 2 n-2. And then you usually sort of, in all the historic constructions, you wouldn't do something derived. You would just compose functors, and that just forces you into the semi-simple world. So to summarize, this includes all, to my knowledge, currently known TQFTs in dimension strictly greater 2. Even dimensional TQFTs in dimension strictly greater 2. Okay. So that's the setting we're working in, is these semi-simple TQFTs. It's sort of, if you want, an interesting representation theoretic condition. And now let's completely switch gears, right? We've talked about this representation theoretic condition on TQFTs. Okay, let's move aside and let's do something completely else. Let's go to the side of manifolds and talk a bit about surgery theory and talk about a specific sort of example of surgery theory. Namely, let's talk about stable diffeomorphisms. Two close connected to n manifolds, M and M prime, are stably diffeomorphic if there exists a natural number so that if I take M and connect sum it up with Sn times Sn. So I remove a disk from the manifold, and I remove a disk from Sn times Sn, and I glue these two manifolds together along the boundary. If that becomes diffeomorphic to n connected sum with the same number of copies of Sn times Sn. Okay, that's the notion you can define. The reason this is an interesting notion is that the classification of the stable diffeomorphism classes of manifolds, especially in dimension 4, is much easier than the classification of diffeomorphism classes of manifolds. And essentially, this is reducible to a Bordism problem. If you're somewhat familiar with surgery theory, what happens is if you use that notion, somehow you don't have surgery obstructions. If there's sort of a way to do surgery theory here where you essentially don't have obstructions. And so this classification is much, much easier. This is especially true in dimension 4. In higher dimensions, it turns out that, for example, for simply connected 6 manifolds or higher even dimension, stable diffeomorphism is the same as diffeomorphism. So in higher dimensions, these notions start to converge, and you don't actually see that much of a difference. That's why somehow higher dimension manifolds are easier to understand. In 4 dimensions, they are like really apart from one another.
From what dimension they coincide? I didn't hear it.
So 6 or higher even dimensional manifolds that are simply connected are stably diffeomorphic if and only if they're diffeomorphic. The k is just a natural number. There just has to exist. Oh, you just connected some k times. You take it, connect it on, and then you connect it on k times, yeah. Yes. It's a k-fold sum, yep. Okay. Here I say, much easier, it's still not easy. But you move into the world of homotopy theory and algebraic topology, and that makes it somehow, in principle, computable, even if the actual computations you have to do are still difficult. And you move away from weird behavior in 4 dimensions.
So K is the same on the left and the right?
K is the same on the left and right. That's not very important. You can have both notions, and essentially it gives, the only difference is that if K is not the same, you can change the Euler characteristic, and that's the only difference. But if you record the Euler characteristic, then it doesn't matter whether they're the same or not. So it's not that important. It makes the theory a bit cleaner. I think originally it was sort of defined with different Ks, but I think with the same K it's a bit cleaner. Yeah. Okay, so theorem number 1. Semi-simple even-dimensional TQFT, so this is why I'm talking about this notion, only see the stable diffeomorphism type. So that's something you can show. If I have a TQFT that's semi-simple, this is a representation theoretic condition, then it sort of has this effect that it only sees manifolds up to stable diffeomorphism. Okay. Yes?
What does this mean in dimension 4?
We'll get to this. So I get to some examples where one can do some concrete computations once one knows this. Exactly. And what I want to say is this theorem, the proof of this theorem, this is in 4 dimensions. This is in this first paper that I mentioned in higher even dimensions. This is with Chris Chomapris. In the second paper, the proof of this theorem really just uses the definition. So we really just use what it means for two manifolds to be stably diffeomorphic, and you really check that you can sort of do some calculations, and essentially it boils down to in a semisimple algebra, in a commutative semisimple algebra, you don't have nilpotent elements, and somehow this is sort of a nilpotent phenomenon that one's seeing here, right? So that's very, very roughly what's going on, and you really just do some Bordesman computation, and then that follows. Okay. So now you could use, well, fine, okay, semisimple theories don't see stable diffeomorphism type, but maybe semisimple theories don't see anything interesting at all. Maybe this is still a far too sort of fine equivalence relation. Maybe I should sort of quotient much, much more. I shouldn't just look at up to stable diffeomorphism, but up to something much, much weaker. So you could ask, is this upper bound on what semisimple theories see? Is that optimal in some sense? And the answer is, and this is really what happens in the second paper, is yes, it is optimal, assuming some mild finiteness condition. If M and N are two manifolds that are not stably diffeomorphic, and if these manifolds are sufficiently finite, I'll say in a second what that means, then there exists a semisimple TFT that distinguishes these two manifolds. Okay? So what does sufficiently finite mean? This is only for the experts, it's not very important. It means that the fiber of the classifying map of the tangent bundle of M, of this 2N manifold, has finite homotopy groups in dimension 1 up to the middle dimension, up to N minus 1. And for example, in 4 dimensions, this is just saying that the fundamental group of the manifold is finite. And that's not a very, very bad condition. And in fact, the sufficiently finiteness condition, I think in many examples that we've tried, you can also drop it. It's not a necessary condition for this theorem, but it's a sufficient condition for the theorem. So I don't, sort of, once you move away from it, you have to sort of do a case-by-case thing. I don't know how to do this generally, yes.
So when you prove this, do you use like some well-known and established TQFTs that exist in all dimensions, or how do you?
I'll get to this. This is the second part of my talk. So the second part of the talk is sort of focusing on this one. This one I won't actually explain how I prove it, even so I like the proof, but this is, for example, in this paper, you can find it. Yes?
In the theorem 1, this is about the whole TFT and not just this algebra that you mentioned.
This is the whole TFT, yes. It's if I have an even-dimensional TQFT, which is semisimple in the sense that these two algebras are semisimple, then if you give me a 2n manifold, another 2n manifold that is stably diffeomorphic, and I want to look at set of this one manifold versus set of this other manifold, these two numbers will be the same. That's the statement. Yes? Yes, everything here is for even-dimensional TQFTs. I only define this notion of semisimple a priori for even-dimensional TQFT. Of course, you could sort of think about what it would mean for odd-dimensional TQFTs, but the surgery theory with the stable diffeomorphisms works cleanly with even-dimensional TQFTs. And what I find just sort of, as a takeaway, what I find surprising about this is really, there is this notion, really representation theoretic notion of a TQFT being semisimple, and there's this sort of manifold theoretic notion of two manifolds being stably diffeomorphic. And it's quite neat that these two notions really match up in this nice way. They really sort of seem to agree in a sense. And I'll say a bit more about this philosophically later. So now I've first come to the first question that Catherine was asking, which is, what can we learn about manifolds, or what does that tell us about these TQFTs? So the first thing to say is, in 4 dimension, if I have and these are just now consequences, because again, this classification of manifolds up to stable diffeomorphism has been well studied, and you can just take these results and translate them now over into results about TQFTs. So for example, semisimple 4-dimensional TQFTs, they cannot detect smooth structure on oriented 4 manifolds. So if I have two oriented 4 manifolds that are homeomorphic but not diffeomorphic, these semisimple TFTs will give the same number. They won't notice that they have different smooth structure. This is something that was sort of expected, I think, in the community, but this gives a proof of that. On the other hand, there do exist examples of unoriented 4 manifolds that are homeomorphic but not diffeomorphic that can be distinguished by semisimple theories. So this is something that I think goes against something that sort of people tend to think or say, which is, oh, you know, TQFTs don't see smooth structure, these TQFTs that we currently have that are defined on all manifolds. That's true for oriented manifolds, but not for unoriented manifolds. There are examples of these manifolds, namely, an easy one is RP4 itself, and this is an exotic smooth partner, and these can be distinguished by semisimple theories. Now you could also ask, does it just depend on the homotopy type for the oriented ones? There are examples of oriented manifolds and oriented TQFTs that can distinguish homotopy equivalent but not homeomorphic for manifolds. So there are examples where it really sees the homeomorphism type and not just the homotopy type of a four manifold. And on the algebraic side, you learn something about the TQFTs as well. For example, if you look at things like Crane-Yetter theory or other state-sum constructions in 4 dimensions, where you start with a non-modular ribbon fusion category. If you start with a modular category, there were formulas for what it assigns to manifolds, which depend on the signature and the Euler characteristic of the manifold. But if you start with a non-modular category, it was just not known what this would see. And you can now use this classification, and you say, actually, it just depends on the stable diffeomorphism class to sort of re-engineer formulas for the value of Crane-Yetter theory on a bunch of manifolds. So for example, on simply connected manifolds, 4 manifolds, you can again write down a formula which now depends, again, signature Euler characteristic, and it depends very sensitively on whether the manifold admits a spin structure or does not admit a spin structure, so there's some additional subtlety coming in, but you can like write down these formulas very explicitly. And if you go to higher dimensions, so this is all results in 4 dimensions, if you go to higher dimensions, in fact, it turns out that the semi-simple TQFTs, they can distinguish some exotic spheres, for example, in dimensions 8n plus 2. You can build semi-simple theories to distinguish exotic spheres. In fact, I was saying earlier that 2 simply connected manifolds are stably diffeomorphic if and only if they're diffeomorphic. So 2 exotic spheres are never, if they're not diffeomorphic, they're not stably diffeomorphic, because of course spheres are simply connected. The problem is this finiteness condition, which doesn't hold for spheres, right? Because this finiteness condition is saying that the map from the sphere, a classifying map of the tangent bundle, has sort of finite difference up to the middle dimension. And the problem is that in BO, at some point you have a set appearing. This sort of mirrors the string group discussions that we had. And that set, of course, isn't in the sphere, so the difference is infinite. And that sort of breaks that. But you can get around in a bunch of examples by just sort of mapping forward to something which is slightly more finite, and then you can still distinguish some of them. Yeah, okay. So this is the first answer, and then there was your second question, which was, how do you prove that? How do you prove the second theorem? And let me get to this. And the way we prove this is that actually we use the classification of stable diffeomorphism classes of manifolds. And this classification is very classical. This is due to Matthias Craig. And so let me sort of recall this a little bit. And this is sort of a nice and easy part of surgery theory, where we don't have to do L theory, we don't have to do obstructions. It just all works really cleanly in that world. And let me briefly recall how this works. So our proof relies on this classification. To understand this classification, we first want to understand 2 notions. 2 notions that have come up before, I think in Conrad's talk, for example. Namely, first, the notion of a tangential structure. For us here, a tangential structure is just a map from some space X, space in the sense of homotopy theory, to BOD, to the classifying space of the orthogonal group. Examples of this are, for example, BSOD mapping to BOD, this classifies orientations. B-spin-D mapping to BOD classifies spin structures. Of course, you could also do B-string-D mapping to BOD, classifying string structures, and so on. And on the other side, we can look at X structures on a manifold. What we have to do there is we have to take the tangent bundle, which is an OD bundle, and we have to lift it up along this map to an X bundle, if you like, right? So this is and this is what it means to be an orientation or spin structure or principal G bundle. You can sort of encode this in terms of this notion of tangential structure, and it's really just sort of a lift of this map in the homotopical sense. Equivalently, if you don't like these classifying maps, you can think of this data as encoding a space with a homotopy coherent OD action. This is the fiber of this. And then you can think of an X structure as really giving you a map from the total space of the frame bundle on the manifold. So the frame bundle, right, a point in it is a point in the manifold together with a basis for the tangent space. And this is a total space. This total space of the frame bundle has an OD action by just rotating your frames. And what the data of this is just an equivariant map from the frame bundle to F, which is OD equivariant. Okay. Great. So this is tangential structures and X structures on a manifold. And so now let's get to the actual classification. For that, we need to understand one additional notion. And this is the notion of the tangential K-type of a D-manifold. So if I have a D-manifold, again, we have this classifying map of the tangent bundle. It's a map from the manifold M to BOD. And what we can do with maps between spaces, between homotopy types, is we can always factor them. We can factor them into a surjective map followed by an injective map. When I have a map between two sets, I can always do the image factorization. I first have a surjective map, and then I have an injective map, which just includes the image of this map into my target. And I can do just the same with homotopy types, but there I have to decide at which, or with spaces, with topological spaces, I have to decide at which level I want to have the surjective injective factorization. So a map is called K-connected if it's an iso on low-dimensional homotopy groups, and if it's surjective or epi in dimension k plus 1. I mean, don't pin me down on the k's and k plus 1s and k minus 1s here. There's a lot of confusion in the literature on how to count these things. But the idea is this is surjective on level k plus 1, and it's an iso below. On the other side, you're injective on level k plus 1, and it's an iso above. So you do sort of a stupid factorization on high levels and on low levels, and at level k plus 1, the level you're interested in, you do surjective, injective. Okay, and this is something you can always do with a manifold, or with a map of between spaces. And in particular for a manifold, you can always sort of get this thing out. And we will in particular care about the tangential n-1 type. Again, this is where sort of most of the story sort of happens in the middle dimension. So we take this 2n manifold and we factor it so that this somehow records, this looks very similar to the manifold in low degree, and it looks very similar to BO2n in high degrees. And in the middle dimension, there's sort of this difference going on. And the first thing to point out is that if you look at this diagram, if I start with a manifold, I extract such an X, I do this factorization, I should say this factorization is unique up to homotopy, then I can think of this manifold as having a canonical X to BO2n structure. Because this dashed map here is a lift, right? This is sort of my map X to BO2n, and I lift it up here. So for every manifold you give me, there is a canonical structure associated to this manifold, such that this manifold has this structure in a canonical way. Okay. X is uniquely determined up to homotopy. So you can have if I have another one, a y, such that I factored through it, and I have a homotopy equivalence from X to Y that makes this triangle, or these sort of two triangles sort of agree. Yeah. It's precisely like you would do it with sets and functions and sort of surjective, injective, just that now you have to sort of think of a set as being actually a homotopy type or topological space, and as a function as being a continuous map, and then so it's the same uniqueness. Yeah. Okay, so now here's the theorem that was proven by Matthias Craig in '99, which is saying here's first a map we can define. We can look at sort of the set of stable diffeomorphism classes of 2n manifolds, and on the other side we can look at another set for now, which is X, sort of spaces X, which have a finite n skeleton, and such that the map from X to BO2n is n-1 truncated. So it's of this form. It's a mono on pi n, and it's an iso on higher homotopy groups. And in addition, we can look, this is sort of a set of a bunch of data. The other piece of data we remember is a Bordesson class in a certain Bordesson group. In a Bordesson group of manifolds with X structure. It's sort of a slightly subtle Bordesson group, because again, I want to remember some unstable information, some Euler class. So if you're an expert, this is really defined to be pi 0 of a Madsen-Tillman spectrum. If you're not an expert, you can think of this as just it's a certain Bordesson group of manifolds with X structure. And you have this map. What does this map do? It takes a manifold, M, it does that factorization, it records X to BO2n, this is the first piece of data, and then it notices, oh, M itself has an X structure. And so now I can think of the manifold up to Bordesson with that X structure. Previously, I've thought of it almost up to diffeomorphism, up to stable diffeomorphism. Now I just remember this X mapped to BO2n and the Bordesson class of the manifold, but not the Bordesson class of the manifold as a manifold or as an oriented manifold, no, as a manifold with this X structure. So that's a map you can build. This is fairly easy to explain. The thing that's non-trivial is that this is an isomorphism. This is a bijection of sets. So this data completely describes the stable diffeomorphism class of a manifold. I just need to know what's somehow the lower half homotopy type of the manifold with its map to BO2n, and what's, if I think of this as a tangential structure on the manifold, what's the Bordesson class with that structure. These are the two pieces of information I need to remember. Okay, and this tells us how we go about constructing these TFTs. Because what we now do is build TQFTs, build semi-simple TQFTs that can understand this data. And this is sort of different to the first proof when we say that semi-simple TQFTs only see stable diffeomorphism type. This just uses the definition of connected sum and as n times as n. And now we're really using this classification and trying to build TQFTs that see that data. And then we know they see the complete stable diffeomorphism time. Okay. And just to say, this data is, for example, in 4 dimensions, it's not scary. It sounds a bit scary, or homotopical at least, but it's, I mean, the finite n skeleton with this n-1 truncated map really in 4 dimensions is, for example, is a finitely presented groupoid with an action of this 2 group, right? The 2 group being C2 cross BC2. So it's a very easy type of 2 group. So there's not much data here. And this Bordesman class, for which you have to understand this Bordesman group. But that depends, of course, on what F is and what the action is. Okay. But this is something you can just sort of compute with. Like, you can do it with cross modules or however you like, but it's like algebraic data that's accessible, and you can write down formulas for it if you like. Okay, great. So, how do we build these TQFTs? What we use for this is a generalization of the idea of Dijkgraaf-Witten, generalized by Kontsevich, Fried, Quinn, a lot of people, which go under the name, or you could call them finite gauge theories of finite sigma models. So we're essentially doing the homotopy theorist version of what a sigma model is. And this goes as follows. What we start with input data is a space X together with a map to BOD. So this is a slight generalization of what's usually in the literature that we need to use here. It's something that's sort of twisted by this OD action. Usually you would just have a space as input. Now we have this additional map to BOD. This is a map from X to BOD, and we require this map to have pi finite fiber. What does pi finite mean? Pi finite means it's a space whose all homotopy groups are finite, and such that only finitely many of these are non-zero. At a certain point, it just becomes 0. Equivalently, you can think of this as a pi finite space with an OD action, if you like. And this pi finite space F you can think of as sort of being the target space. And the OD action might be trivial or might be not trivial. If it's sort of if it's trivial, it gives you sort of a more classical sounding type of sigma model. And the other input data is an X-structured TQFT. And what you can extract from this is a TQFT which is defined on unoriented manifolds. I mean, more generally, you can do this sort of relatively. If you go from an X to a Y, you can go down here. So I have this X-structured TFT. Well, how do I define it? On closed manifolds, I can tell you what it is. What you do is you sum over all possible X structures on that manifold. You have some normalization factor that you need. It's not important what it is. Here's the formula for it. And then you evaluate the other TQFT that you've given yourself, W, on that X-structured manifold. So sort of really a naive thing. I give you a closed manifold without structure, I just sum over all possible choices of X structures, and I evaluate my X-structured TFT on that guy, and then I have a normalization factor that I need to make this into an actual TQFT. What's slightly more difficult is to see that this is a TQFT. I've just given you a formula for closed manifolds. Yes?
So how is this related to Quinn TQFT?
Yes. So Quinn TQFTs arises, or is sort of a special case for this if X to BOD is of the form Y times BOD, and just being the projection map. So in some sense, you can think of this as being an OD twisted version of Quinn's TFT. Quinn just sums over maps from M to Y, but here we're summing over X structures on M, and somehow maps from M to Y, just a sort of ordinary sigma model. You can think of these as being a special case of a structure on a manifold. It is a tangential structure, but it's a very sort of boring tangential structure. But other examples are, you can think of X being B spin, for example. Then you would sum over spin structures on a manifold, and this is something that Quinn's TQFT cannot do. Or you can sum over string structures or orientations or whatever you like. The important thing only is that the fiber has to be finite, because that's what you sum over in the end. So if that's not finite, you have infinite sums. So that's somehow the condition that these sums work. Okay, and let me just point out, you can think of this as being a finite version of a path integral. So this is my space of fields. It's the X structures on my manifold. And I think of this just as a homotopy type, so I'm really just working in homotopy theory here. And this normalization factor is sort of a measure, a type of counting measure on my space of fields. It's uniquely determined to be, I mean, I have to use this to make it a TQFT. And so I can take sort of these two things, I could sort of just write as an integral over the space of X structures, and then I evaluate my big theory W on it. So, right, and this is an OD twisted version of a construction of these people. Yeah, so that's the construction. Those are the TQFTs that we're using. And a way you can, yes, yes.
So that's one thing. So you have the W, which is already a TQFT.
Yes.
And then you're building another TQFT.
Yes.
And where do you get the input one from?
Yes, that's a great question. This will be answered on the next slide. Exactly. So this is the right question. So the way you can think of this, what I've just done is I've just explained to you that if I give you, or if you give me a W, an X-structured TFT, I can produce for you an unstructured TFT. And this is in some sense subtle because the sort of naive map goes the other way around. If I have an unstructured theory, I can always get an X-structured theory which just ignores the X structure. So what you should think of this as sort of a wrong-way map. This is in some sense a sort of, if you want to think of TFTs as a sort of very weird sort of cohomology, this is somehow a push-forward map in cohomology. It's a fiber integration map. And this needs this finiteness condition. This is where these sums come up. So it's sort of, this is what this construction does for you. It takes this X-structured TFT and it integrates out the difference between X and BOD and gives you an unstructured theory. But you asked the right question, why is that useful? It's only useful if you have access to interesting X-structured theories. But we already know, we've already seen some examples of interesting X-structured theories, namely invertible theories. And so what we are going to use is we're going to use invertible Ws. We use invertible Ws because those we can understand, and then we feed them into this machinery to integrate out this fiber, and that gives us a non-invertible theory downstairs. And why can we do this? Because invertible theories you can classify. And for this, it's very useful to use the target SVAC, because there this classification is even easier. Namely, here's a theorem. I think this was sort of folklore for a time. I think that the actual, like the first real proof of this is in a paper by Fried and Hopkins on reflection positive theories. And this theorem says the following: if I look at an invertible theory, which is defined on X-structured Bordersons, to SVAC is really important here. There is a map from here to just homomorphism on the X-structured Borderson group in the complex numbers, which is basically, I mean, more or less you can think of this as take the partition function, just evaluate the theory on closed X-structures manifolds and see what it is. Because it's invertible, this will just depend on the Borderson class. This map is an isomorphism. So if I know what it does on closed D-manifolds on sort of elements in this Borderson group, I know what the whole theory is. This really uses SVAC. This really uses that the target is super vector spaces. And this gets us going, because now we can just take a character on this Borderson group, produce from it this invertible theory corresponding to it, feed it into this Dicraft-Witten construction, or this generalized Dicraft-Witten construction, and get an unstructured theory out. Okay. So why is it useful? Why does that tell us these stable diffeomorphism classes apart? This is now I mean, now we've access to a whole lot of semi-simple theories. It turns out they are always semi-simple if I start with something invertible. I don't say this on the slide, but this gives us a whole collection of semi-simple theories. And now let's see why these semi-simple theories are useful to detect these sort of stable information, the stable diffeomorphism information. And so let me sort of do this on a slide which sort of tries to get across the message, the basic idea that I want to get across today. What we've just seen is that invertible supervector space value TQFTs are dual to Borderson classes. Right? This is really a Pontryagin duality. This is sort of Borderson classes, and I'm just dualizing into some C cross, and this is what invertible supervector space value theories are. So there's really a duality here, okay? Now we could look at different data. Here we could look at this data, namely a Y to BO2N, which is N-1 truncated with Y, a finite N skeleton, and an element in this Borderson class. This is the data that corresponded to what a stable diffeomorphism class of manifolds was, right? This is what Craig told us is the data we need to try to detect. On the other hand, we were talking about this input data to this Dicraft-Witten construction. There I told you what you need to input is a map X to BO2N. It doesn't need to be N-1 truncated, but let's just assume that. And it has pi finite fibers. And the other piece of data that we needed to input was an invertible field theory. In general, a general field theory, but let's just input an invertible theory. An invertible theory is, as I just said, just a character on this Borderson group. But now this starts to look curious, because the things we're seeing on this side pretty much look like the things we're seeing on that side. Up to a little duality here. Here it's a character, here it's an element of this Borderson group. And so what we sort of expect is, well, maybe these two sets or spaces are actually, again, dual to one another. And it does turn out there is a sort of Pontryagin duality you can build that tells you that these are in perfect duality up to this finiteness condition. Namely, what is this pairing? This pairing is precisely doing what this Dicraft-Witten theory was doing. It takes an X and a W and a Y and a M here, and it pairs it together by doing this finite path integral, and it just takes M here, it pushes it, or it pulls, well, depending on how you want to think of it, you sort of pull back, you know, this is okay, let me say it again. You take this sort of sum, this finite path integral, you sum over all maps from y to x over BON. You can take this m, you can push it forward along one of these maps. If you have a y structure, then you will always have an x structure if you fix an f in here. And then you evaluate it with w. So just bring it over to the other side, evaluate these, sum them up. And this, you can prove, gives you a perfect pairing. It's a duality pairing between these two things. So now we're getting to a point where we see, okay, this is how the proof then works in the end. We sort of use these things, this is what dichrofitting theory is doing, and it perfectly pairs up with the data that Craig tells us sort of completely classifies manifolds. And we're doing this sort of weird sum, where we have to sort of sum over all possible maps from y to x to sort of be able to compare these two elements. Okay. But now, let me just sort of end on a few comments sort of related to this. So, and I should say here, this is, of course, a surjection, right? There's more data here. You can sort of just remember the Borderson class if you like. This is if you want an inclusion. But really what we've been seeing is that there was a map from stable diffeomorphism classes to this data. This map was called take the tangential n-1 type. This map might seem very destructive. You essentially just remember or algebraic topological information, right? You remember somehow the homotopy type or something built from the homotopy type, and you remember a bit of Borderson information. And it's in some sense a miracle, or rather surgery theory, that tells you that this map is actually a bijection. And this is what Craig has been doing. Okay? But we've also talked about something else when we talked about theorem 1, which was, well, if I have this data, I can produce from this data a semi-simple TQFT. So there's a construction, which is this finite gauge theory construction, which produces a semi-simple theory. And for every semi-simple TFT, we've seen that we get stable diffeomorphism invariance. And so if you look at this diagram, you could ask, well, is the left column really completely dual to the right column, right? And more precisely, if this is an isomorphism, if Craig tells us this is an isomorphism, should we dually expect that that is an isomorphism, right? This sort of really suggests that. And should we really say, okay, let's look sort of what happens here, the fact that this is an isomorphism, that's surgery theory. Is there something analogous on this side? Is there something dual to surgery theory that tells us that every semi-simple TQFT actually arises from one of these guys? And this is sort of the question I want to end up on, which is the question, is every semi-simple TQFT said of this form, of the form ZXW for some X to be for one truncated and W invertible? Is it always a dichrofitting theory, a generalized dichrofitting theory? The answer is I don't know. I don't even know how to extract X and W. But if I do allow myself once extended theory, a theory which is valued in superalgebras or in superlinear categories, then we claim the answer is yes. This is a theorem in progress. Details need to be worked out, so please take this all with a grain of salt. But what we claim is that if I have a once extended TQFT from board 432 to S superlinear categories, that's the same data as a map from some, well, there's some groupoid X to BO4. So this is really a groupoid with the C2 cross BC2 action. And invertible theory, so in other words, a character, so that you can get your theory back by doing this summation, this integration procedure. And this proof is purely algebraic. It does not use the stable diffeomorphism classification. And it's really a statement about the target being superlinear categories. It's really important that you use superlinear categories here and not linear categories, say. So it's really the super is again important. And in some sense, if you look at the proof of the theorem, it does very much feel like it's dual to what Craig has been doing in the surgery proof. I can't make this precise yet. Again, I want to stress, this does not use the stable diffeomorphism classification. It's something that's just happening sort of on this side here of the chart. But it would be very cool if one could really sort of implement it in such a way that these two proofs are in the end the same proof. And that I don't know yet. But that's the end of my talk. Yeah, thank you.
Are there some obvious generalizations to this kind of twisted twin TQFT? Or is it somehow, is there a reason to think this will cover everything, or this is sufficient to cover everything, or is it just the first step?
Yeah, that's a good question. So here you could already ask So here I'm requiring, this is something I sort of swept under the rug a little bit, I'm requiring that this map is n-1 truncated, so that, say, very explicitly you start here just with a one groupoid with this OD action rather than a pi finite space. So the first thing you could ask is, well, what happens if I start with something which isn't a one groupoid? I can also just sum maps into something which isn't a one groupoid. And then this theorem tells you actually that wouldn't see more. Every TFT, even if it's sort of, you map into some large space where homotopy groups vary in sort of arbitrary levels, for example, Quinn theory, you could still re-express it by summing into some one groupoid, in some twisted way. So this is sort of getting at, sort of to here. So there are some naive generalizations you can think about, but somehow, if that isn't a, sort of, at least if you're once extended, where I believe this is an isomorphism, all these sort of naive extensions would still fall back into this world. And there would be a way to extract from this more complicated data this sort of slightly more easy data. So I think you really have to push completely out of that world. You really have to do something which isn't just finite sums of finite things. Yeah. From a once extended perspective, again, I think what you have to do is you really have to work sort of, the most obvious or most naive next step would be to say, you don't end up in superlinear categories. And so what could you end up with? Well, you probably should end up in DG categories or some superversion of DG categories and work derivedly. But then I think all these sort of finite sums, they sort of really work finitely and they work non-derivedly. And so I don't actually know whether there is a generalization of this Quinn type construction in a derived world, for example. And it also from if you think about sort of this perspective again, at least if you're once extended, I claim there is sort of, these two things are in that sense also in perfect duality. So on this side here, you have something which sort of surjects to here, which is all manifolds, diffeomorphism classes of all manifolds, surjects onto stable diffeomorphism classes. And on this side, you could now ask, okay, what's the thing that sort of injects back up? Like in this, you could say, oh, this sits in all TQFTs. So maybe there should be a TQFT, and those are then sort of dual to all diffeomorphism class of manifolds. But you didn't really have to start to see more data than that data, because that data is the stable data. You have to start to see data that's somehow not accessible by standard algebraic topological surgery theoretical methods. And somehow these finite path integral type constructions, they are built from that data, so I don't expect them to see more than homotopical data, or this sort of homotopical plus Bordesson data. Yeah.
Maybe I missed the point, but this construction of this field in ZXW.
Yes.
Is this one of the state sum model theories, or is it something different? Because it looks so similar, like this summing over.
Yeah, you can write this as a state sum. Becomes a bit complicated because then you have to like sort of give yourself a combinatorial description of this homotopy type. I think it's the way I like to think of this is it's sort of a finite homotopy theoretical version of essentially a sigma model of geometric quantization. So, for example, the thing you assign to an M to D-1 manifold is really global sections of some line, of some vector bundle, of some line bundle if W is invertible associated to, yeah, sort of this data gives you some local system, you take global sections of that local system.
So here D can be odd also.
Here for this construction D can be odd, yeah.
Is like Dirac-Witten theory, is that an example of this?
Yes. Dirac-Witten theory is the example where X is of the form Y times BOD and Y is BG. So really where X is of the form BG times BOD. And then you're just counting maps from M to BG.
And this character is something like this cocycle?
The character is the cocycle, that's right. Because the cocycle gives you a Bordesson invariant. It gives you this invertible theory. So this is just more general.
Dirac-Witten, I think to be precise, a homotopy 2 type is a group, a module,
Yes.
a chronology class.
Yes.
They took the module to be trivial action. That's,
Yes.
In that sense, there's
Yes.
a special case of the general construction.
Yes. No, I think of it slightly, I agree that you can think about it this way, but I don't, so just to translate it into this world here, I do retain, so the cocycle, I don't do the sort of associated extension of BG by that cocycle. Rather, I remember BG and the cocycle, and what the cocycle is doing, it really does, I'm really thinking of this as this character. So this is the TFT, this is the thing that I'm integrating down. This is the co-cycle. And I'm really just, again, my X here in the Dirac-Witten case is just BG times BOD. So it's not this two group that you're talking about, it's just BG.
You're using a very special.
It is as general, but it's just where the data lives. So what you're saying is that, so Dirac-Witten is sort of, you have BG to say, I mean, if you're sort of in dimension 3, you have BG to KT3, and you can take the fiber of this, and this is some Z or X or whatever, and this is the two group you were talking about. This is G and...
That's where G acts on C cross trivially. That was my point.
That's right. That,
You could instead take a principal bundle over BG and take a section of K.
Yes, and...
Of the vertical.
That's right.
That's the fully general case.
That's right.
So
And
this is just a very special
that's
case
right.
of
And
the general two types.
that's right. And more generally, you can take...
Basically, to open up a book that had been, they couldn't be bothered learning what a two types are.
Right.
They rediscovered a special class of homogeneity.
Right, yes. And I mean, more generally, what we're using here is, let's see, we take BG, and then from this data, you get I mean, in this case, for BG structured X manifolds, you get a character on this by taking M, and you just do M to BG to K. I mean, this M has a map to BG because it's in here, to K C cross 3, and then you evaluate this against the fundamental class. And in what Esra was just saying, you could do the same there as well. I mean, if this was your two-type, you would sort of have manifolds with sort of structure in this two-type. I think you can do the same, and that gives you a character. And that's important data that we need to extract. Is this character on a Brodersen group? But I mean, you can sort of move it around, but in the end, what you want to extract is you still want to keep BG sort of having it sort of split up in this way and the character.